Good morning, everybody. I wanted to give you a quick pre-lab video to walk you through the process of the unknown experiment. Since there's not a lot in the written procedure, I know some of you are feeling pretty anxious, so I wanted to get something out there to help everybody feel a little more prepared when you get to lab on Tuesday. What we're doing is a kind of modified version of a qualitative analysis of organic compounds. What do we mean by qualitative analysis? Well, as far as analysis goes, we're trying to get the chemical composition of the sample, but being qualitative means that you're using non-numerical means. Some of you may have done this in general chemistry, or in your high school chemistry, where you had an unknown solution and you added a bunch of whole different chemicals to it to make different colored precipitates, and that told you which cations and anions were present in the sample. Well, you're going to do the same thing here with organic molecules. Now, when you're doing a qual analysis, you're going to use things like melting point, boiling point, and solubility, and compare them to standards to help identify organic molecules. In a strict qualitative analysis, you would also use things like chemical tests, and I'll show you some examples of those in a little bit. And those would indicate the presence or absence of functional groups. Now, before, say, 1940s, when we got IR, and then the 1960s, where we got NMR, qualitative analysis schemes were really the only way that you could identify any organic molecule. And these were very time-consuming because you had to require many individual tests to compare to the standards, or you had to decompose a new molecule back to already known standards and compare. And this was a very time-consuming endeavor. And if you actually, just out of curiosity, go to the library databases and pull up the Journal of Organic Chemistry, if you pull a paper from, say, the 1930s, and then, say, you pulled a random organic paper from 1935 and looked at what they did to explain how they made a certain molecule, and then compare that, look in 45, 65, 85, 2005, 2015, you'll see that over those 10-year intervals, there were leaps and bounds of difference made in the complexity of the molecules that could be made, and the certainty with which the number of molecules that could be made, and the certainty with which those molecules were identified. So why do we have to do it in Chem 212? Well, a lot of reasons. First of all, because all of you are going to be given two compounds, a liquid and a solid, and each of you is going to have a completely different liquid and solid. This is going to be an excellent independent project. As much as I've stressed to you guys to kind of focus on working in your own hoods, focus on what you're doing, not spend so much time comparing what you do to other people, not worry so much about things are good and bad, a lot of you are still having trouble doing that. So this exercise really pushes you to be independent in your lab work. The other thing is you are going to need to manage your own project. You're going to have 9 hours of lab time, and then you're going to have time outside of lab where you can take melting points and IRs and do your analysis, but you're going to need to figure out how to manage that time in order to get this done. You're going to need to make careful observation because I'm not going to be over your shoulder, and even if I'm around, if I have 20 students each analyzing 2 unknowns apiece, I can't keep track of 40 experiments that I'm not seeing. So when you ask me questions, I'm going to come back to you and want to know what you observed. And along with those observations are going to be your good record keeping. The idea that you're going to need to jot down what you're doing and what you're observing. Now, don't get so tied up in writing in your notebook that you don't get the lab work done. So you're going to be wanting to do these 2 careful observations and good record keeping, but it's got to be done within the project management side of it. Finally, critical thinking. The idea that you're going to actually need to think critically about the data that you're collecting. And sometimes that data that you collect is going to be disparate, either because the molecule itself behaves strangely because the molecule has impurities, or maybe because you haven't executed the test well. You may have data that points in two directions, and you're going to need to evaluate which piece of data you have more faith in and more confidence in. Confidence is probably the better word. And finally, the idea of discussing your project with another person. When you talk to the lab aides or you talk to me about your project, about your unknowns, you're going to need to walk me through it from the beginning. You're going to come into my office and want to talk about an NMR, and I'm going to say, stop. Take me back to the beginning. Is this your solid or liquid? What was it soluble in? Because in order for me to understand the context of the data you're showing me, you have to bring me that context. And again, because there's going to be such a large number of you analyzing such different compounds and going about it in different ways, you're going to have to tell me what's going on in an intelligible way. So in your procedure, I've actually given you a fairly good plan for doing this lab. I actually despise doing this because it really takes out the idea of you managing the project for yourself. But I realized I needed to do this in order for this to be accomplished in the 3 weeks that we've allotted. You'll notice that I have in-lab times. So this is your first 3-hour lab, your second 3-hour lab, and your third 3-hour lab, what you need to be doing. And if you follow this layout, March 19th, you may not need to be in lab at all. If you've actually done fairly solid work up to March 19th, you may be repeating experiments or repeating IRs, or you might have to purify a derivative, but you should have not much left to do on March 19th. Notice the amount of things that you're going to need to be doing outside of lab. These are going to be things that you can do that are not wet lab and that can be done in your room. For example, IR and melting point are things that you can do outside of lab, or you can do outside of lab hours. You can come to 213 and do that on your own. A lot of these other things are things like analyzing data, determining functional groups, coming to office hours and confirming things, consulting tables, making lists of structures, beginning interpretation. These are all dry lab things that you need to do outside of lab because you don't want to waste your in-lab time on the 13th when you need to be synthesizing, because you can't do that any other time, drawing lists of structures. That's a real waste of time. Spring break is right in the middle, so there's stuff that you're really not going to be able to be doing. And so notice your checklist for outside of lab is running from the 27th to March 2nd. And notice that you don't pick up your next batch of things to do until March 13th. I like breaks to be breaks, so you'll notice there's really not a list of things to do during your spring break week, and hopefully you won't need to. You're going to do weekly notebooks still, March 13th, 19th, and 27th. As talked about in the procedure, you're going to be writing more in a narrative format that you came in and that you did things and what your conclusions are. I strongly suggest that when you do this, that you make each experiment a separate notebook entry with its own title, with its own data, and with its own conclusion. So, for example, melting point of solid, IR of liquid, boiling point of liquid. Each of these would be titles of 3 individual notebook entries. And so for the week of March 13th, when you turn in notebook entries on March 13th, you may be turning in a whole lot of notebook pages because you might have the melting point, the solubility in the IR of your solid, the boiling point, the solubility in the IR of the liquid. So you could be absolutely turning in 6 notebook entries on March 13th. But again, how much you do or don't get done in a given week is up to you. Now I want to walk you through some of the steps that you're going to do this qualitative analysis. And the first thing that you're probably going to need to do is figure out the functional groups that are present in your molecule. Now, thinking in terms of qualitative analysis, we kind of act like the world was before IR. And the idea that before IR you did this by doing solubility tests or what we call the chemical tests or the colorimetric tests. You're going to get a taste of using solubility in this lab. I've posted some videos and examples of how to do colorimetric tests, but that's not something that we're going to do because it's really not a modern skill. What you're probably going to learn after you've done your solubility tests and your derivative is that you're going to learn that you really love NMR, that you really love IR. A lot of you have a hate-hate relationship with IR, but I think after you see what life was like before it, you're going to appreciate it. I've got some links showing how to do a chemical test and showing you how it's done. I'll put those links on Canvas if you want to take a look at them. What we mean by chemical tests is the idea that if you had your unknown, you would put it into a test tube or into a series of test tubes. And then you would say, okay, I want to know if I have an alcohol. So I'm going to do a chromic acid test. And the idea is that in this test tube, you would add a solution of chromic acid to it. And if the chromic acid turned from pink to brown, that would indicate that there was an alcohol, because the alcohol would react with the chromium 3+ cation, which is pink, and it would turn to the chromium, I think it's a chromium 1 cation that is brown and rusty looking. And so if you saw that color change, you would know that you had an alcohol. And you would probably run 2 different tests so that you could confirm for sure whether or not you had an alcohol. Then you would get out a couple more test tubes and, oh look, chromic acid, a positive chromic acid test indicates that you have an alcohol or an aldehyde. So your results from this test you'd need to use to think about your aldehyde. You'd also maybe run a 2,4-dinitrophenylhydrazine test and decide whether or not that test was positive or negative based on whether it changed color or a precipitate formed or whatever. Then you would need to rule in or out an amide, so you'd get out a bunch more test tubes. And you would run an alkaline hydrolysis test in this test tube and evaluate those results. Then you might need, ruling in or out whether or not you have an aldehyde. You would then move on to the amine tests and get out a bunch more test tubes and run a bromine water test or a basicity test. So what you can see is what you would need to do to determine a functional group purely qualitatively and purely using chemical tests is something that we used to refer to in lab as the 12 test tube nightmare. That you've got this whole series of test tubes that you're adding drops of different chemicals to, and in the real world, you would have to make all of these solutions up. These aren't necessarily things that you can buy. And then you would have to do all of these things. And then try to interpret the results. And especially where you have tests that can give positive results for more than one functional group, you can see that it gets a little crazy. I think we can all agree that an IR is a lot easier. The other qualitative way that you can determine functional groups, and one that you are actually going to be doing, is the solubility test. And the solubility tests are going to take advantage of some of the things I've been teaching you in lecture to help narrow down what functional group you have. So what you have here is a flow chart, and you're going to go in with water. And if your solid or liquid is soluble in water, then you can conclude that you have one of these functional groups. Now, what's interesting about the water solubility is notice that all of these tend to be the little bitty small ones. And what this is the idea that in these small molecules to 1 to 5 carbons, your London dispersion forces aren't very strong. And these are all polar, possibly hydrogen bonding functional groups. So what you've got in all of these cases is you have functional groups that have a little bit of hydrogen bonding capability, but if they're small enough that their London dispersion forces aren't very strong, that you could actually be water soluble. What happens if you're water insoluble? Well, now you're going to get out some 5% hydrochloric acid and you're going to run another test. And you're going to look to see, am I soluble in that hydrochloric acid? And it turns out that amines are soluble in aqueous hydrochloric acid. Why? Because they aren't dissolving in this hydrochloric acid as much as they are reacting with the hydrochloric acid and making an ammonium ion, which is soluble in water. So if you're soluble in hydrochloric acid, you can conclude that you have an amine. What if you're not soluble in hydrochloric acid? Then you're going to have to try another test with 5% sodium hydroxide. And you'll notice that these functional groups, the strong and weak acids, the carboxylic acids and the phenols, tend to be soluble in 5% sodium hydroxide. I wonder why that is. Now, there is a distinction that we make with the sodium hydroxide test. Things that are soluble in sodium hydroxide, which is a very strong base, may or may not be soluble in 5% sodium hydrogen carbonate, which is a weaker base. And that's going to let us tell the difference between the carboxylic acids and some of the phenols, although the phenols can be a little bit ambiguous here. Last but not least, if we're still insoluble in sodium hydroxide, we've probably got a very neutral compound. And so what you're going to do is react it with concentrated sulfuric acid. This isn't going to be desk reagent. This is going to be a dropper bottle of consulfuric. And most of you noticed while you were doing your hydrolysis your dehydration reactions last week that concentrated sulfuric acid is pretty nasty. It dissolves paper towels. And so you can make a distinction on functional groups between consulfuric as to whether or not it actually has some functionality or it doesn't have any functionality. These solubility tests should not take you very long, and your procedure outlines for you what indicates a positive solubility test. You should be able to knock out your solubility test for both your solid and your liquid on the first day of lab. Now, between the chemical tests and the solubility tests, again, qualitative analysis is how I learned to quit worrying and learn to love my spectroscopy. Because IR is quick and easy. Some of you don't make it quick and easy, but it is. You go in, you make one sample, you run one spectrum, and you get out a printed piece of data that you can take back to your room and analyze on your own time. The other thing is that you can see more than one functional group present. If your molecule happens to have, say, a carbonyl group and an aromatic ring, you will see evidence of both the carbon-oxygen double bond stretch and the various stretches that we see from the aromatic ring. The carbon-carbon stretch, the sp2 hybridized C to H stretch, the out-of-plane bends, and the overtones. So you can see more than one functional group at a time with an IR, whereas with chemical tests, that's why you have to run so many tests. One other thing that you're going to do in this experiment is you're going to make something called derivatives. And your derivatives are going to be used to verify identity. And the point behind a derivative is you're going to have some unknown compound. It might be a solid, it might be a liquid. And you're going to run a reasonably simple chemical reaction on it that's going to make a derivative of it. It's going to slightly change the functional group. And when you change that functional group, what you're going to get out of this derivative is a solid, which is going to be reasonably easy to purify. And the idea behind getting a solid that's very easy to purify is that you're going to be able to get very good melting point data of it. Then you're going to take that melting point data and compare it to big tables of standard data for compounds. Okay? And this will make more sense in the context of the example that I'm going to show you in the next video. A couple details about derivatives is that you've got to know the functional group of the unknown so that you can choose the right derivative. And I will show you this in the context of the example that's in the next video. So I'm going to go ahead and stop with this video. I'm going to start up a new video where I'm actually going to walk you through the steps for a fictitious unknown. And hopefully that'll help you understand what we're doing. Thanks for watching, and I will see you on Tuesday.